friction drag and pressure drag. As we have mentioned, the theory of drag is weak and inadequate, except for flat plate. Except for flat plate. This is because of low separation. Quadrillary theory can predict the separation point but cannot accurately estimate the pressure distribution in the separated region. The difference between the high pressure in the front stagnation region and the low pressure is the near separated region cause a large drag contribution and called pressure drag. Let me write the pressure difference between the high pressure in the front stagnation region and the low pressure in the rear separated region. The low in the rear separated region. Cause a large drag contribution called pressure drag. This is added to the integrated shear stress of friction drag, so plus integrated shear stress friction drag of the body. Which is often CD we have to drag pressure plus drag of friction. The relative contribution of friction and pressure drag depends upon the body's shape, especially its thickness. Proportional to the body shape especially thickness. The next page shows a picture drag data for a streamlined cylinder of very large depth into the paper. Let me provide the picture here. This figure shows drag data for a streamlined cylinder of very large depth into the paper. At zero thickness, the body is a flat plate and exhibits 100% friction drag as shown in this picture. Friction percentage of the total drag. We have pressure plus the drag from friction. This is at the 0 point, zero thickness. At thickness equal to the chord length, simulating a circular cylinder, the friction drag is only about 3% in this case. T on C, the ratio of T on C show here. We have 0 point here and the circular shape at the front of the streamlined cylinder. Friction and pressure drag are about equal at thickness T on C equals to 2500. Note that the drag force coefficient in the picture B, were shown here, looks quite different when based on the frontal area instead of plane form area. Plane form being the usual choice for this body shape. The two curves in this picture represent exactly the same drag forces. Thickness ratio, we have based on frontal area, based on plane form area, two type of area that we discussed before. Frontal area provide the information from the streamline in the front and investigated the front area of the body, and the plane for area investigated from the above. Anyway, we have two diagrams for drag force for this type of streamlined cylinder in two approaches of area definition. There is also another example that's shown in this picture. This picture illustrates the dramatic effect of separated flow on the subsequent failure of boundary layer theory. The theoretical in-seat pressure distribution on a circular cylinder will be discussed in chapter 8. It's shown as the dashed line in this picture. We have the relation for pressure Cp for pressure coefficient and the stream specification, which is equals to where P infinity is P and V are pressure and velocity. In the previous stream, the actual laminar and turbulent boundary layer pressure distribution were shown in the picture C here are startlingly different from those predicted by theory. Laminar flow is very vulnerable to the adverse gradient on the rear of the cylinder, as shown here. We have the Cp in values theta. For example, we can calculate the values Cp from 0 to 180 degrees from this diagram. This diagram shows the minimum pressure coefficient at the 90 degree. Laminar flow is very vulnerable to the adverse gradient on the rear of the cylinder, and separation occurs at about theta equals to 82 degrees, which certainly could not have been predicted from an implicit theory. The broad wake and very low pressure in the separated laminar region caused the large drag coefficient. The turbulent boundary layer, as shown in this picture, is more resistant, and separation delayed until there. For laminar and turbulent, we have theta equals to 120 degrees with the resulting smaller wake. Higher pressure on the rear and 70% leg drag. We have drag coefficient in turbulent flow 3/10 in comparison with the 1.2 drag of laminar flow, so the turbulent flow provides smaller drag coefficient. This explains the sharp drop in drag at transition point from the turbulent to laminar to turbulent flow. The same sharp difference between vulnerable laminar separation and resistant turbulent separation can be seen for a shape also here.